how is it different for other atoms? So it turns out to be a decent approximation to other atoms. You can assume these orbitals are fairly similar in shape to those in the hydrogen atom. The difference is, in a hydrogen atom, the 2s and the 2p have exactly the same energy. 3s, 3p, 3d, exactly the same energy. The energy does not depend on your subshell number, which is why those never showed up in the Rydberg equation. All you saw was the principal and the quantum number, because when it jumps up to the n equals 2 level, it actually could be in either a 2s or a 2p. There are 4 different choices for it, but they all had exactly the same energy. In multi-electron atoms, then the 2s, 2p, 3, they don't all have the same energy. These are not on the same scale. The energies are different here than the hydrogen atom. But you see there's trends. We'll talk about trends soon. There you break the degeneracy in the energy level. You get different energy levels. And so the reason is you get shielding and essentially an effective nuclear charge. These outer electrons that are in, say like the 3p orbital, the electrons from the 2s orbital are down there beneath them, and they're screwing up with the attraction. You no longer have the same energy interaction with the nucleus, and so you get different energy levels. And so the nice patterns we saw in the math for the relatively simple equations we saw for Schrodinger's equations just go out the window. They're no longer there. It's much more complicated. You have to use big computers to figure them out. And but we can calculate them. Like we've got, for any atom, we can calculate all the energy levels with arbitrary precision at this point. Just you need to throw it into a computer to solve the Schrodinger's equation at that point. The one exception is if you have hydrogenic atoms. If you might notice, then the label for that demo was hydrogenic atoms. And that's because if you have helium or lithium, they'll have the same patterns because there's no other electrons to get on the way. You can actually use the Rydberg formula. The only difference is you got to multiply it by 4 in the case of helium or helium plus, or 9 in the case of lithium, because it's multiplied by the number of protons squared. So helium has 2 more protons, so it has 4 times, the energy levels are 4 times bigger. And lithium, there's 3 protons, 1 electron, lithium 2 plus. So you get, it's 9 times bigger. We don't really talk about that much because notice it's lithium 2 plus. You probably have seen by now that generally you just see lithium in a +1 state. You very rarely see it in a +2 state. It's hard to get that out. You can get it, but it takes a lot of work. So it's more of just a curiosity to know that, yeah, actually it does have degenerate energy levels. They're just a lot bigger energies because you have a +3 charge attracting a -1 electron. And yeah, so what we'll be doing in chapter 9 is talking a lot about these energy differences and how they affect the periodic table. Yeah, so filling orbitals starts to explain the periodic table. We'll talk about this more next time, but yeah, refresh your memory and see if you can, notice the patterns here that, 10 electrons here, 6 here, 14 here, 2 here. Coincidence? Obviously not. And so we'll talk more about exactly what those consequences are when we discuss the next chapter of the book.